Divisibility rules are taught in every middle school math class, yet I can guarantee that you don't know some of the most simple rules. Sure, you know the rules for 2, 5, and 10, and maybe you even know them for 3 and 9, or 4 and 8. But do you know the rules for 7 and 11? What about 13 and 16? In this video, I'm going to explain not only how to find these rules, but how to calculate them easily in your head. Over the next 10 minutes, we're going to fill this page with rules. And we'll start with 7, not only because it's probably the only single-digit number that you never learned the rule for, but also because learning this rule will help us create all the other ones. To find our first rule, we want to be able to split any number into the number of tens it contains and the number of ones. The number of ones is easy, that's just the last digit. And we can see, using 154 as an example, that the number of tens is just the remaining digits. By taking off the last digit 4, we're left with 15. If we take 15 times 10, we get 150, and adding 4 brings us back to our original number. This can be done for any number, no matter how long it is, and the fact that these numbers here are much smaller than the original is why divisibility rules are so easy to use. So now we have found for any number, just by looking at its digits, we can split it into 10 times a number plus another number. We're going to call these numbers A and B. A represents all the digits of the number up to the ones place, and B is that final digit. If we can find that this expression, 10a plus b, is divisible by 7, then the original number is as well. The trick here is to multiply by 5. If this expression, 50a plus 5b, is divisible by 7, then 10a plus b is as well. Our next step is to split 50a into 49a plus 1a. We do this because 49 is a multiple of 7, 49a is always divisible by 7, no matter what a you choose. And now, the only way the whole thing can be divisible by 7 is if a plus 5b is. A plus 5b might not seem that much more helpful than 10a plus b, but remember that a can be really long, while b is only a single-digit number. So we are more worried about multiplying a by a number than b. For 154, we know a is 15 and b is 4, and to calculate a plus 5b, we do 15 plus 5 times 4, which is equal to 35, or 5 times 7. Since our result is a multiple of 7, our original number is as well. If you take a really large number, your result will still be a really large number, but you can keep repeating the process until you get to a number that you recognize. We can use what we learned for 7 to find the rules for the other numbers, starting with 2. If we look back to our 10a plus b expression, we can notice that for the same reason that 49a is always divisible by 7, 10a on its own is always divisible by 2. No matter what you plug in for a, it will always be 2 times 5 times that a. Therefore, our number is only divisible by 2 if b, its last digit, is as well. The same logic, by the way, can be used for 5 and 10. They will also always divide 10a, and therefore a number will only be divisible by 5 or 10 if its last digit is. For 5, this means the last digit must be a 0 or a 5, and for 10, it can only be a 0. Before we continue, let's just mention briefly the 3 easiest rules. The negative numbers follow the same rules as the positive numbers. For example, since we know 154 is divisible by 7, we know it is also divisible by negative 7, and that negative 154 is divisible by 7 and negative 7 as well. So we can basically ignore the negative when we're dealing with divisibility. We also know that 0 does not divide any integers, and 1 divides all integers. Moving back to the more interesting cases, let's look at 4. In the same way that we split up our numbers into the last digit and everything else, for 4 we split up the last 2 digits and everything else. Take this relatively long number. Since we've moved a digit over, we have to multiply the long string of digits by 100 instead of 10, and then add 51 like usual. We do this since 100 is divisible by 4, so this whole product is as well. You can probably start to see the pattern here. We use the information given by the digits to split up our number into as large a multiple of 4 as we can, plus a much smaller remainder. Then, since we know it divides that large multiple, all we have to do is check the remainder. In this case, we just have to check if 51 is divisible by 4. It is not, so therefore the whole number is not as well. Next, let's find the rule for 3. Instead of splitting up our number into 10a plus b, or 100a plus b, let's keep each digit as its own power of 10. We turn this into 3 times 1,000, plus 8 times 100, plus 4 times 10, plus 6. And what we have to do is, just like before, pull out as many multiples of 3 as possible. Since 100 is equal to 999 plus 1, we can turn 3 times 1,000 into 3 times 999 plus 3 times 1. We do the same for the other multiples of 10. 8 times 100 becomes 8 times 99 plus 8 times 1. And 4 times 10 becomes 4 times 9 plus 4 times 1. And since 3 divides 999, 99, and 9, we can ignore those terms, and we only have to check 3 plus 8 plus 4 plus 6. This, you might recognize, is just the sum of the digits. This rule also works for 9, since it also divides 9, 99, 999, and so on. The sum of the digits in that case has to divide 9 instead of 3. Next up we have 8. In the same way that we found our rules for 2 and 4, we can represent our number as 1,000 times a long string of digits plus 592, the last 3 digits. 8 divides 1,000, so all we have to do is check that it divides those last 3 digits. This isn't the easiest one to do in your head, but it's certainly easier than trying to do the whole long division. Our final single-digit number is 6. 6 is a composite number that is the product of 2 different prime numbers, 2 and 3. We can therefore say if a number passes our test for 2 and 3, it must be a multiple of 6. Note that this only works if your composite number is a product of 2 different primes. If we look to the double digits, we'll start moving a lot quicker because of all the composite numbers. For 12, we can check 3 and 4. For 14, we can do 2 and 7. 15 is 3 times 5. 18 is 2 times 9. 20 is 4 times 5. 21 is 3 times 7. 22 is 2 times 11, which I'm aware we haven't found yet. And 24 is 3 times 8. Notice that for a number like 14, 2 and 7 are our only options. But for 12, for example, we could have tried 2 and 6. However, this would not have worked. Since 6 is checking for 2 and 3, if we tried 2 and 6, we'd be checking for 2 twice, which, as we said before, doesn't actually work. This is why you couldn't do 4 and 6 for 24, since they share a common factor of 2. But you can do 3 and 8. Moving on to the few numbers that we have left, we can find a rule for 11 that is difficult to find, but easy to use. If we take our number 3,762, just like before, we can turn it into 3 times 1,000, 7 times 100, 6 times 10, and 2. Just like with 3 and 9, we want to turn those big numbers into multiples of 11, but it's a little bit more complicated. For 3 times 1,000, we turn it into 3 times 1,001 minus 3 times 1, which again we can do since 1,000 is equal to 1,001 minus 1. 7 times 100 becomes 7 times 99 plus 7 times 1, and 6 times 10 turns into 6 times 11 minus 6 times 1. 1,001, 99, and 11 are all multiples of 11, so we can ignore them, and we are left with negative 3 plus 7 minus 6 plus 2. This is similar to our rule for 3 and 9, but it alternates between addition and subtraction, which we call an alternating sum. This alternating sum of the digits must be a multiple of 11. In this case, they sum to 0, and since 11 times 0 is equal to 0, the sum is a multiple of 11, and so 11 divides 3,762. Moving on to 13, in a similar way to 7, we're going to take our number in terms of 10a plus b. Just a reminder, b represents the last digit, and a is everything else. We multiply this expression by 4, which gives us 40a plus 4b. We split 40a into 39a plus a, and since 13 times 3 is equal to 39, all we have to do is find whether 13 divides a plus 4b. Next up we have 16, which, as another power of 2, requires an even bigger power of 10 to check divisibility. Taking b as the last 4 digits this time, we represent our number as 10,000 times a long string of digits, plus the last 4 digits, 1684. 10,000 is divisible by 16, so we only have to check 1684. Determining whether a 4-digit number is divisible by 16 is probably the most difficult rule on the list, but it is simpler than checking the whole number, and unfortunately is the best we can do, since the 10a plus b method that we've been using doesn't work well with most even numbers. For our next 3 numbers, we're going to have 3 very similar rules, so let's go through them quickly. For 17, we multiply 10a plus b by 5 to get 50a plus 5b. We turn 50a into 51a minus a, and then since 17 times 3 is equal to 51, we only have to check negative a plus 5b. Since a is potentially a really big number, we really don't want to make it negative, so we use our negative number rule from before to multiply this expression by negative 1 and get a minus 5b. For 19, we multiply 10a plus b by 2 to get 20a plus 2b. By now you can probably see where I'm going with this. We split it into 19a plus a plus 2b, and obviously 19 divides 19a, so we only have to check a plus 2b. And for the last of our primes, for 23 we multiply 10a plus b by 7 to get 70a plus 7b, which we turn into 69a plus a plus 7b, which we can show leaves us with a plus 7b as our rule. Finally, we arrive at 25, and we make b represent the last two digits again to give us 100a plus b. 25 divides 100, meaning we only have to check that the last two digits are divisible by 25. The only two-digit numbers for which this is true are 0, 25, 50, and 75, and with this, we've come to the end of our list. If you want to try to find more rules for yourself, I've calculated the rules up to 100 and put them in the description if you want to check your work. The divisibility rules can be incredibly helpful for very little work, so I hope learning about them was both useful and interesting. As always, thank you for watching, and I'll see you in the next video.